Next, we're going to learn how to work with quadratic functions in factored form. Notice we still have a leading coefficient. This will tell us if our graph opens up or down and if we have a stretch or compression vertically. Also, instead of knowing where the vertex is, we know where the zeros are, so we will know where the graph crosses the x-axis. We can turn those into ordered pairs. Our y values will be 0. We've seen this before when we were solving quadratic equations in factored form. Our essential question today is how do we graph and write equations of quadratic functions in factored form? Starting off, does our graph open up or down? We have multiplication by a negative, so our graph will open down. The x-intercepts will be when we set the function equal to 0, we will solve for x. The negative out front is really a -1, which can never equal 0, so we will simply set those two binomials equal to 0. Remember, the zero product property says if you have multiplication and the answer is 0, one of the things you are multiplying by must be 0. So in our case, either x is -3 or x is 1. Those give us our two x-intercepts. Remember, we started by subbing 0 in for f of x. So when we write those ordered pairs, we need 0 for our y value. To get the axis of symmetry, it will fall right between the zeros. Remember, our parabola is symmetric, so points on either side of the vertex have the same y value. We take those x coordinates, add them together, and divide by 2. In our case, we get -2 divided by 2 is -1. So the axis of symmetry is x equals -1. We use that x coordinate to find the vertex. Remember, the axis of symmetry goes through the vertex. So the equation for the axis of symmetry gives us the x coordinate of the vertex. We simply substitute that back into our function for x. Everywhere there was an x, we will replace it with -1 and solve for the y value. So we have the opposite of 2 times -2, which gives us 4. Writing that as an ordered pair so we can plot that point, we have -1, 4 for our vertex. And the other point we will use to help us graph our function is the y-intercept. This is when we substitute 0 for x into the function and solve for y. In this case, we have the opposite of 3, or -3, times -1, which is 3. So our y-intercept is 0, 3. Plotting all of those points on the graph, we had two x-intercepts, one at -3 and one at +1. Our vertex is at -1, 4, and our y-intercept was 0, 3. What we can do is use that axis of symmetry that goes through the vertex to flip that y-intercept across the vertex to get our fifth point, so we can graph our parabola more accurately. Notice those x-intercepts are reflected across the line of symmetry, as well as that y-intercept. Taking a look at domain and range, it is a quadratic function, so our domain is all real numbers. And our graph opens down, so our range is less than or equal to the y-coordinate of our vertex. Second example, this time our leading coefficient is positive, so our graph will open up. Those x-intercepts, if we set each binomial equal to 0, we would have -2 and +2 for our x-intercepts. Make sure you put those as ordered pairs. It comes from setting the function equal to 0 and using the zero product property. To get our axis of symmetry, we add those x-intercepts together and divide by 2. In this case, we get 0 divided by 2, or 0. To find the vertex, we substitute that value back into the equation for x and solve for our y value. Here we would have 3 times 2, which is 6, times -2, which is -12. So our vertex is 0, -12. Finally, our y-intercept, substituting 0 for x, which we just did to get the vertex, we would get -12. So the y-intercept and the vertex are the same in this case. Plotting those points, our zeros were at -2 and 2. Our y-intercept was at -12, as well as our vertex. So we will sketch our parabola. Notice that the leading coefficient for our parabola was 3, which is a vertical stretch by 3, which means our graph is very skinny, which we can see. Domain for quadratic function is all real numbers. Range, since our graph opens up, would be y is greater than or equal to the y-coordinate of our vertex. Writing the equation in factored form is similar to writing the equation in vertex form. So we start by looking at the generic equation for factored form. Remember, C and D are those x-intercepts. So we'll start by subbing those in and their opposites. We have 1 0 at -4, that will go in as a +4. We have another 0 at +5, that goes in as -5. The other point that we are given will go in for x and y. That 6 will go in both spots for x. The -3 goes in for y, and we'll solve for a. Simplifying inside those parentheses, 6 plus 4 gives us 10. 6 minus 5 gives us 1. So we have 10 times a. Dividing both sides by 10, our leading coefficient is -3/10. Summing those back into our equation with the x-intercepts of -4 and +5, again going in as opposites. Finding the domain and range. Domain, all real numbers, it's a quadratic function. Range, we need to identify the y-coordinate of the vertex. I'm going to estimate it off the graph. It looks like it's a little bit bigger than 4, so I'm going to say y is less than or equal to 4 1/4. That is just an estimate based on what I see from the graph. One more example of writing equations. This time we only have one x-intercept. So what we will do when we sub that into our equation, we will use that one x-intercept twice. Subbing that x-intercept in, it was negative, so it goes in as a positive. Our other coordinate, the x value is -5. We're solving for a, and our y value is 3. Solving for a by starting inside those parentheses, -5 plus 2 gives us a -3. -5 plus 2 gives us another -3. Multiplying those together, we get 9. And dividing both sides by 9 and simplifying, we get 1/3 for our a value. Subbing that back into our function with our x-intercepts, we get x plus 2, and we can simplify that to squared as it repeats. Finally, determining our domain and range. Parabola, so the domain is all real numbers. Our range, we do have the y-coordinate of our vertex this time. The graph opens up, so it's greater than or equal to 0.